Now let's understand um, the extended topic of basis expansion. Let's understand the splines, okay, the regression splines, piecewise functions, step functions, and other stuff. Those all are definitions basically, but I'll try my best to give you an elaboration on those topics. Okay, so let's start it. So first of all, I'll elaborate what do you mean by linear regression again. So this is an introduction to linear regression, which is the base of this chapter. So we are talking more of linearity in this chapter. uh, we are talking about nonlinear function, linear function, but still all the same, all these things holds the property of linearity. Okay, even though we are talking nonlinear, but still it should hold the property of linearity. This is the intention of this chapter. So now linear regression, if you understand, linear regression is mostly used for statistical technique, and it is mostly used for prediction, for predictive modeling or for prediction purposes. Okay, it is a supervised learning algorithm which is having real value output, increasing or decreasing output, like that. Okay, it is a linear model. Besides that, it is a linear model, and it is having a linear relationship between your dependent variable and independent variable. So if I have an equation y equals to mx plus c, then in this equation your x is the independent variable. This x is your independent variable, and your y is basically dependent variable. And why it is dependent? It is dependent because according to the value of x, your y is going to is going to vary. Okay, vary according to the y with x variable. But the relationship between y and x, the relationship is basically linear relationship. This has to uh, understand here. This has to be formulated as this is a linear relationship between your dependent variable and independent variable. And if you see, if we go for multivariant analysis, then your equation is going to be changed from single variation to multivariate equation. So it is going to be like m1 x1 plus m2 x2 plus m3 x3 plus mk ck. Okay, this is a multivariant equation where let me write it down, where these m1 m2 till mk are nothing but coefficients. Sorry, not this is not ck, this is xk, but the coefficient of x, and these x1 till xk are nothing but feature in your data set. I hope you understand it. Okay, so all these features are having some coefficients, and when I say coefficients, these coefficients are nothing but weights. Okay, so you can change it, you can write this m1 as coefficient, or you can write it as a weight. So every feature is having some weight associated with it. You getting it? So every feature inside this data set, every feature has some coefficient, and let me write as weight associated with it. Okay, this is important. Every feature have some weight, and based on this weight your feature is going to be vary. Okay, so if an equation is like, how can you can compare your feature from other feature, like you can compare your x1 feature with x2 feature. And how can you compare? The according to the weight. So if m1 feature, sorry, if m1, that means the weight, is greater than m2. Okay, so if the weight of this m1, or the coefficient value of this m1 is greater than m2, that means what it resembles, it says that the feature x1 has higher importance. X1 feature has higher importance compared to compared to x2. This is what it says. So if your one weight is very higher than the other weight, then you can say that the feature associated with that weight, that higher weight, is going to be having higher importance than that of the other feature. This is what it says. So this is the linear regression that we use for prediction purposes. But however, this linear regression is having some problem associated with it, and there are many problems actually. So let me just go further. And what are those problems? The first problem is in its predictive power. Now the problem, or you can say the limitation of linear regression comes in predictive power. Okay, so what do you mean by predictive power? So the prediction that you are getting from the fitting your model, the prediction that you are getting, the result that you are getting, it is just the linear combination. Okay, so when I say it gives you some predictive power, but this predictive power is nothing but the limitation. And why it is a limitation? Because this predictive power from the linear regression is nothing. Here prediction is nothing but the linear combination. It's nothing but the linear combination of your dependent variable, the independent variable and your dependent variable, nothing but the x and y relationship. So that means if it is linear combination, that I can say then it is nothing, just an approximation of statistic analysis. So it is just an approximation. Okay, it is nothing but just an approximation. And if you are working with approximation, then I don't think this is a good result, right? This is not what we want. I mean, it gives you definitely some good approximation, good output, good accuracy. However, we cannot rely on approximation. It is sometimes poor one, which we don't want it, right? So and why we do not use this approximation as our result is because we are, first of all, we are not doing anything like a very we are not doing like what you can say, higher mathematics. Like we are just using some linear models, and we are getting some approximation that we call it as prediction, but it is not going to be a good one. And why it is not a good one is because if you apply a small mathematics, then it gives you some output, right? If you apply a higher method, I can simply write it down here, like if you apply simple mathematics, you are getting some result, you're getting better result, let's say. And tomorrow, let's say tomorrow, if you apply on the same problem, if you apply tomorrow on the same problem, if you apply higher mathematics, then it will give you some result, but the result is going to be best as compared to the better result. Can you see? If you increase your mathematics here, it will give you some best result compared to the other one. So that means it is just the mathematics that I am getting the result. Okay, so you can apply derivative function, you can apply calculus function, and you will get the best result. However, there is no such there is no such what you can say, the proof of concept that it is the best result that I am getting. You're getting the result, but it is merely the linear combination of your dependent and independent variable, and it is just the mathematics that you are changing. Okay, so if I am using linear function, and tomorrow if I use polynomial function, then it will give you some good result. But then there are some problem with polynomial function too, just like it overfits your model. So what I mean to say is, I hope you are getting it. Okay, so from linear regression, now let's say if we go for polynomial regression, So let's say your linear regression is not working because it's just merely an approximation. So if you go for polynomial regression, then polynomial regression is doing nothing, but it just add an extra predictor. And what is this extra predictor? So if in linear model, if I'm using x, this is LR, then in polynomial regression, if this is x1 feature, then in polynomial regression I'm doing nothing but just adding an extra predictor. This is an extra predictor and it is in PR, so polynomial regression. This is what I'm doing. So if my equation in linear model is x1 plus x2 plus x3, then in polynomial regression it is x1 square plus x2 cube, x2 quadrate, like that. Okay, so I'm just increasing the power to the original. I'm adding an extra predictor, or you can say the original power to the original predictor. This is, so your equation for the response variable or y variable is going to be, let me write it in m term only. So this is m0 m1x plus m2 square plus m3 x cube plus so on. This is going to be your polynomial regression. So you can see that if you compare it with your linear regression model, so this is your linear model. So this is your PR, this is LR, and only difference is you are adding the power to your original predicators. So these are original predicators, but you're just doing the adding an extra predicators. Now if you see both these things over here, you had seen the equation, but now if you see the graph of these two equations, then what will happen is, just change the color over here so that I can show you. So if you see the linear regression graph, and if these are the points that you are getting, sorry, not getting, but these are the points that you had scattered or plotted, then the line that you will get is, let's say this is the regression line. Okay, so this is x2, this is x1. Now if you see, this is linear regression, and the same thing if you apply for polynomial regression, what will happen is, this is polynomial regression, and if these are the points, okay, these are the points, and the polynomial regression line is going to be like this. This is the polynomial regression line. This is also the x2 and x1, the same original predicators, and this is my PR. But then if you see, this is completely, this is okay model, this is good model. However, if you see, there is a high variance, and that's why it is an overfit model. Okay, and I don't think I can use this overfit model. However, I can use this good model, right? So if you increase the power of these original predicators, it will give you some good result. Definitely, it will give you the best accuracy, but it will lead to, these curves lead to overfitting, okay, which is not flexible for my problem. So I will not use it, right? So we go for linear regression, but then there is a problem of the predictive power. It doesn't give you the good prediction, it just merely give you an approximation. Then we go for higher mathematics, and then we apply this polynomial regression. We add an extra power to that original feature, but then what it gives you, it gives you better result. However, it gives you an overfit model, which I don't need it, right? So this is the problem for polynomial regression. So what we can do to deal with this polynomial regression, so we can do is, we can separate the data set. Okay, so these data points you can see over here, these are completely scattered over here. Now what I'm gonna do is, I will make these separable data set. I'll create the bunches of these data set, and then I will apply the small polynomial, very piecewise polynomial, to these small data sets. Okay, So I hope you are getting it. What I'm saying is, the polynomial regression, what polynomial regression is doing is, it takes the complete data set and it adds some power to the feature, and then those powers on the feature is going to be my new variable, right? So if I'm starting from the first point, so if I use linear regression, then I have some features, right? And then those features are my old features. And then if that linear regression is not giving me the good accuracy, then what I'm doing is, I'm I'm adding some power to those features. Okay, but those are my old features. In that old feature itself, I'm adding some power, and those power is going to do is, it gives you some accuracy. However, it overfit the model. So uh, we have to improvise this thing too. Okay, we have to reduce the overfitting, and this polynomial regression is, however, not giving you the thing that you want, right? So we have to improvise our technique or regression technique. What we can do to improvise, as I told you, that we can separate out some bunches of data points, and those, like what you do in that technique, a cross validation technique, right? You separate out testing and then training, like that. Okay, k-fold clustering, k-fold cross validation you are having. In that, you are taking small bunches of data points. So instead of taking one complete model or one complete entire data set for that modeling purpose, if you are taking the complete data set for that modeling purpose, now what you are doing, you are dividing the data set into multiple bunches, and those bunches are nothing but bins. Okay, so let me write it down here. To overcome certain issues, of polynomial regression, which uses, so instead of building one model for the entire data set, now you divide the data set into multiple bunches. Okay, multiple bunches, and these multiple bunches are known as beans. Okay, or you can say multiple beans. Okay, so these are the beans. And then what you can do is, then you can create individual model for each beans. Okay, and individual model or separate model for each beans. This complete thing is known as such a technique, or such a technique is known as regression spline. Okay, regression spline. So this is the topic that we are doing here. So this is a regression spline, and it is one of the most important nonlinear regression technique. So if the topic is regression spline, then I can say about that it is most important non-linear regression technique. I'm sorry, I'm a little bit fast over here, but there's some notes, we have to write it down. So it is the most important non-linear regression technique. In polynomial regression, in PR, we generate a new feature. And how we are generating? x to x1 square. So this is my new feature by using a polynomial regression. So this imposed a global structure. Okay, so global structure, which is nothing but a complete model, which imposed a global structure on the entire data set, on the entire data set. And now what we are doing, we can divide the distribution of data into separate portion called as beans, and fit low level or lower degree or low level degree polynomial function on each of the bin. Getting it? So I hope now you are getting it, that let me again just redraw it over here. And what I mean to say is, if I have a data set looks like this, and let me take one more line. I have a data set looks like this. Earlier I'm using this whole complete data set for my polynomial regression, and now what I'm doing is I'm separating it out. So this is going to be my first bin, this is going to be my second bin, and so on. This is going to be my k bin. So this is first bin, second bin, this is my kth bin. Okay, and then on these bin we're gonna apply polynomial regression 1, polynomial regression 2, and polynomial regression k. So individual polynomial regression, small polynomial regression we can apply. So a graph of such is going to be look like this. Okay, so let's say these are some of the data points. Actually I cannot, I'm just trying to put it up. Okay, so these are some of the data points, and now your what you can say, the polynomial function, if you apply it on the entire data set, it's going to be look like this. So this is the entire polynomial regression for entire data set. So this is your polynomial regression for entire data set. Okay, now for the this is x2 and x1, and sorry, this is x1, and I was talking about regression spline. So we have to separate our data set and we have to create the bins. So what regression spline looks like, it is going to be like this. So if your data set is separated, okay, it is in the bin format, and then so I'll apply a small let me point out some more point here so that I can okay. So these are some of more points just for the sake of explanation. Okay, and I will remove this one. I'll remove this one as well. Okay, now for the regression spline, this is going to be look like this. So this is the first, you can say the bin for these the polynomial regression for first bin, and then it is like this, and then it looks like this, and then it is going to be like this. So these are the data points which are covering up, or maybe this is also covering up, this is also covering up, then come to this. So here it is also pointing out, and then again it goes like this. Okay, so this is your regression spline. The complete regression. Your regression spline consists of small polynomial regression. So this could be the polynomial regression 1, this could be polynomial regression 2, and so on. Okay, and the points here, I'll write down here the points where a little bit where the division occurs are known as nodes. So that means the points which is there inside the in the polynomial regression as well as on the regression spline. So that means this point could be a node, this point could be a node, maybe if there is a point, then this also be a node, and so these are nodes. Okay, so which is so these points are dividing the polynomial regression as well as regression spline. So this is known as nodes. Okay. And here we cannot use polynomial function, polynomial regression. I cannot apply the complete polynomial regression. This is just for an explanation, but however, the function that you have to use to model such thing, like these small these small PR1, PR2, you have to apply a very small polynomial regression. So a function which can be used for modeling the line for each bean are known as piecewise function. Instead of polynomial function, what you are using now, piecewise function. So I'm going to write it down here. Here I'm going to take another color and I will write it down that function which can be used for modeling each bin. Okay, each bin are known as piecewise function. Piecewise function. Okay, so instead of using polynomial function, what we are using piecewise function. That is nothing but polynomial function itself, but we are using a separate polynomial function for separate beans. So it is cumulatively known as piecewise function. And there are numerous piecewise function available in mathematics, and the first or the most widely used piecewise function is known as step function. So piecewise, there are numerous piecewise function available in the mathematics market, and the function that we use is step function. Okay, this is widely adopted, this is widely used piecewise function for the modeling purpose. So what is this step function? Okay, step function, it is a function. Okay, it is a function which remains constant. Actually, it is a function that remains constant for a time, remains constant for an interval. That means if I have a graph and I want this, then the entire piece, this step function is going to be constant. So I am having the same values over here. Then this piecewise, so this is PR1, this is PR2, this is again constant. Again you do for small polynomial function, then again it is a constant, likewise. Okay, so this is the meaning of that. So it is a function that remains constant for an interval and we can fit in those constant interval time. So we can So we can fit individual step function to each of these beans. Where is it? Okay. So we can fit individual step function to each of these beans, okay, that we had separated out to impose here. And why are we doing it? To impose a global structure. Okay, global structure, it means I'm not using entire data set to impose global structure. But instead I'm separating out some of the data points to bins, and then I'm applying small step functions to get the result. Okay, and so we are breaking the range of x into bins. Here I can also write it down like we are breaking the feature range, we are breaking the feature range into bins, and then and then fit different constant in each bin. Okay, this is what we do in step function. So step function is a constant function for an duration and we can apply that constant function or a step function in each of these beans that you had created. So in general we have we have a range like c1, c2, c3 till ck in the range of x, and then we can range the feature variable, right? So your step function in general, so if I have various constants such as c1, c2 till ck, then what I can say is this ck doesn't look good, that is ck. Then what I can say, I have to range into the feature x. It's going to be capital X. So I will range it like from C, if C0 is available. So let me also put C0 and C1. Okay, so C0 x should be it is an indicator function I, and this is the condition this C0 x is going to follow. So if x is smaller than constant 1, then this is the range of C0, or this is the function of constant that I am going to apply if this condition is going to be met. Okay, in a very similar way C1 is going to be work. So indicator function, and it is going to be range in between C1 is smaller than equals to x and it is smaller than C2. This is again indicator function. So it is going to be work like c of k x, and the indicator function c of k is smaller than equals to x. So these are the constant step function that I was talking about, and then you can individually apply these constant function into the beans. Okay, you can put, so it returns so what this indicator function is going to return, it will give you the result it will give you the result either 0, output is going to be either 0 or 1. This is going to be your output. Okay, if the condition is true, then it is going to return, if the condition is writing down here, if the condition is true, then it is going to return 1. So if the condition, this indicator condition, so I'm also writing indicator condition is true, then it is going to return 1. However, the indicator condition is false, or if it doesn't hold it, then it is going to return the 0. Okay, in that way you can work. And so if x is smaller than the constant that is there in here, if x value, the value of this feature, if it is smaller than this constant, then it will give you 0, and which is going to assign to the c0x. So this is going to be your constant, okay, c0x. So 0 is going to be c0x. In a very similar way, if this condition holds 1 or 0, then it is going to be assigned to c1x, and according to that your data set is going to work. So c0, c1 till ck is going to be 1 0 1 0 1 0, the output of these. Okay, the output of these the constant is going to be in between 0 and 1. So this is the range that you will get. So the graph that you will get okay, the graph that you will get here, it is going to be, if these are the data points, actually I am just putting these, please mind it, these are the data points. I don't have the good pen to draw it. So these are the data points, and your constant function is going to be, initially it is going to be very low, and then gradually it is going to peak up a little, and then it is again peak down, and then it is going to be like this. So this is going to be your step function or you can say the piecewise constant, nothing but step function itself. So this is a piecewise constant. Initially it is going to be like very narrow down, and then it grabs here. Okay, so the values are here. Now this is a piecewise constant. However, there are some problem with this function too. And the function you can see over here. So initially at some interval it is like 0, and at some interval it is like 1. So this is the problem. So your this piecewise constant doesn't create the continuous output. Okay, it is not giving you the continuous output, and also in this binning technique there is no relationship between your input and output. So I'm going to write it down here, that your binned regression that we are talking about, the binning regression or binned regression, is not continuous. It is a discontinuous process. Why? Because it is here 0, then it is 1 here, then it is 0 again. So it is a discontinuity. So binned regression is not continuous as we want, and is not continuous function of the predicator. This is 0, continuous function of predicator, that means your x. I think it is the function of predicators, I think it is y. So that means there is no relationship, between your input and your output. So this is what I conclude from this. Okay, there is no relationship between your input and output. So that's why this is a topic that you can use, however with certain limitations. So this is also a problem inside this concept. So what you can do is, instead of fitting a constant function over a different beans for a range of x, what we can do, we can use these beans, but we will not apply the constant function, but instead we will apply low level or low degree polynomials. Okay, we already had seen polynomial regression. So what we're going to do, we will take the beans, separated beans, individual bean, and then we will apply low degree polynomials in that region. Okay, and the concept, we can do that with the help of piecewise polynomial. This is the concept. So I'm not going to explain this again because I already had provided you. So what I'm going to do is, instead of using a constant function there, instead of using constant function over separate beans, sorry, it's not over, for a separate bean, for separate beans, you can apply low degree polynomials. Okay, with some condition, and so the all other things are going to be very similar, just the condition that comes. Okay, So here I'm writing the with condition, and how you will apply the polynomial, small polynomial. So if your response variable y is a bunch of two low level polynomials, uh, two low level polynomial, so this is m01 plus m11 x1 plus m21, this is going to be like 2 square plus m31 x33 plus some, this is going to be the error. Okay, this is your nothing but error with a condition, and the condition is going to be if x is smaller than c. Okay, this is the condition. The second bunch or second low level polynomial is going to be m of 0 of 2 and nothing but sorry 1 and 2 x1 plus m22 x2 square plus m32 x, this is 3 2, this is 2 yeah, so 3 square, and then again there is an error, and the condition is going to be if x is smaller than c. So this will give you what piecewise polynomial you will apply according to the condition. Okay, so this is what I can provide instead of constant function. Instead of constant function, you take low level polynomial, low degree polynomial, because we are not using higher dimensions, we are using only 3 dimensions, so you can use that. Okay, and what else I can provide here is now again, if you see the polynomial or piecewise polynomial, this is piecewise basically, so this is piece 1, this is piece 2, and so on. Okay, so you will get different piecewise functions, and you will apply those piecewise function to the data set. Now there is one more thing inside this piecewise polynomial. Again, there is a problem. So if there is con, and then definitely there are some pros and cons available in the topic. So I'm giving you the topic, but again there are some problem, and according to that we are proceeding forward. So this is a concept, these all are a concept for data science, that how you can model things with linear and non-linear techniques for regression or classification problem. So if I'm using piecewise polynomial, then there is again a problem. We definitely have a good solution, but then you have to think about this problem too. So what is the problem? The problem is the discontinuity at the nodes. So if I'm saying that let's say this is the graph that I am talking about, and this is actually I'm separating out. Okay, so these lines are very separable line, and these lines represent nodes. Okay, so this is my node 1 and node 2. So that means the points that is touching to the polynomial function as well as the piecewise polynomial function. Okay, these are the nodes. So if this is the line that polynomial function is giving you, then we have applied a certain other the functions too, and those, let's say this is my piecewise polynomial function, which is touching very near to it, and okay, so this is it. And then again here one more and by the way, there are some data points too. Okay, so it touches the data points. It doesn't mean that there is no data points. There are data points, but I'm not just drawing it. So okay, these are data points. And let's say now another another line that takes the points is like this. Okay, this is another function, and let's say there is one more function and some more data points. Actually, these data points are from data set itself, right? I'm not drawing it right now, but there are some points. So let's say this is the graph that you are getting. So there are 3 functions that I'm putting over here. So what you can tell about this graph is there is some problem. At the very end of the nodes, there is no continuity at the end of the node. So I will write there is a discontinuity. There is discontinuity at the end of node. So this piecewise polynomial will give you the discontinuity at the very end of the node. So if this is the end of a node, then it gives you a discontinuity here and this discontinuity over here. And I need to remove this discontinuity to give the better result. And these conditions, these discontinuity conditions should be avoided, because if you see the family of polynomial, the complete set of polynomial that we are applying over here, as a whole it will generate a unique output for every input. Okay, so whatever the input you are giving, um, according to that it gives you the variations in the result. And if you are using different set of polynomials, then there is a small change in the input, there is a large difference comes in this polynomial set. Okay, so I have to remove the discontinuity at the very end or at the end of these nodes. Okay, I need to make it continuous, and there is something called as degree of freedom inside the concept of this piecewise polynomial. So degree of polynomial means the data points from the data set that we are taking it for estimations. So if I have 100 data points, and from those 100 data points if I am taking only let's say I have only 20 data points, okay, and if I am taking only 12 data points from that, then those 12 data points are nothing but the degree of freedom. Okay, they are used for the estimation of the result. Okay, so if I'm using only 12 data points, then these 12 data points are going to be my degree of freedom. Okay, so let's say if I remove the condition for discontinuity and if I try to resolve it, and if I resolve it like this, so if I use now continuity at the end, then the graph that I will get, it is going to look like this. These are my notes, by the way. So if this is the original graph, then I will get the graph, the continuity graph. I will get like this. Okay, the graph that you had seen in the blue line, and you can see it is somehow continuous, continuously following the previous one. So this is the continuous graph. Okay, and how it becomes continuous, we had put some constraint, extra condition or constraint we had provided over here. We had provided extra, by the way this is constraint and condition that we had applied on this graph, and by which we remove the discontinuity. This extra condition or extra constraint that we had put resolves the discontinuity at the node. But then again there is a problem. And what is the problem? Basically, if you see the graph here, it is not as smooth as the red one. Okay, this is the problem. So it is not smoothen. We have to make it smoothen, and this is the thing that we have to do. And how you can resolve this, and how you can make these smoothen polynomials, how can you do that? By providing an extra condition, extra constraint or extra condition. And what is the condition? You will take the first derivative of both the polynomials at the nodes. So if I'm saying, if I take the first derivative of this polynomial and the first derivative of this polynomial, then the first derivative of this and this should be same, and this is what I meant. Okay, so if you want to, so if I write here, if we want to smoothen the polynomial, then we can do is add extra constraint, and what is that extra constraint? Is first derivative of both polynomial must be same. okay, must be same. And beside this, take a small number of degree of freedom. This is this is the extra constraint that I'm providing to smoothen my polynomial. So now this is the thing, that if my piecewise polynomial give you the discontinuity, then that discontinuity resolve it, and now we are putting an extra constraint to smoothen our polynomial, because my graph was not so smooth, right? And to smooth it, we have these two constraints, that first derivative of both the polynomial must be same and take small number of degree of freedom. And now if you see the graph, your graph now looks like this. I'm not actually drawing any data points here, but understand that there are data points. If this is the if this is the original, I mean this is the polynomial, so it is smoothened, and the another data point, sorry, another polynomial is this one. So you can see here that it is also smoothened. And how it is smoothened? Because I had taken the polynomial, the derivative of the polynomial to be same, and I had taken a small number of degree of freedom. So if I have degree of freedom as 12, so DOF is degree of freedom, then I am taking 10 DO of freedom of it. Okay, so this red color having 10 degree of freedom, and that's why I'm smoothing my graph. And now what does that mean? I can put an extra constraint now. And what is going to be the constraint? Then from those 10 sorry, from I'm reducing more degree of freedom. So let's say if I use only 8 degree of freedom instead of 12, then you can say that my graph is going to be more smoothened. Okay, more smoothened polynomial I can get. So by taking smaller degree of freedoms, then your piecewise polynomial is going to be more of, you know, more, it is getting to be more smoothened and smoothened. And such a piecewise polynomial with a degree m, and with m minus 1 continuous derivatives, you will get a topic called as spline. Okay, this is the topic called as spline. So I'll write it down here, that such a polynomial, such a piecewise polynomial, of degree, this is of a degree m with m minus 1, this is also important, right? This is m minus 1 continuous derivative. The topic that you will get is spline. And you already had seen a regression spline, so this is the spline. Okay, so you can have a cubic spline, natural spline. There are numerous number of spline available, and we can use that spline to smoothen our piecewise polynomial function. So this is the all you know, methods that you can apply for your last chapter. And your last chapter is moving beyond linearity. Okay, so all the chapters that you had seen, they are having more number of linear functions, but in this chapter we had seen how we can use this non-linear function to that can help in building better result in linear models. Okay, so this is the topic, and I hope you understand it. If you have any doubt, you can ask me. This is the topic of also smoothing your what is the topic is smoothing spline. Yeah, smoothing spline. This is also a topic called as smoothing spline. You can look after this, and if you have any doubt, you can comment in the comment section, and I'll be happy to help you. You please go through the cubic spline and natural spline. There are numerous posts available on the Medium and towards data science. This is not in your topic, but smoothing spline and regression spline and spline itself comes under the same category. So please go through that, and if you have any doubt, you please you can ask me. Okay, thank you so much for listening to me.